under the component selection, as I told you, like resistor, capacitor, diodes, even connectors are very important. Okay, so that's the reason I have included connectors this time. And we have like relays, because many of you are like power electronics guys. Even if you are not there, try to use low power inductors, maybe low power relays like 2 ampere ratings or something like that. Because these are used in like many signal switching or something like that. Then we have MOSFET, which is going to be very important, and op amps. So these two are very important. Switching regulators doesn't require that much, because we will be designing the circuits. Then we have PMICs, like multiple outputs regulators, then inductors, LDOs, LEDs, and voltage reference ICs. Just because I am covering microcontroller circuits, so you need some voltage references which can be generated from outside instead of utilizing internal microcontroller reference. Okay. Then we have fuse. All right. So these were the things that we will be covering. Now let us quickly move to the remaining portion of the like LTspice that we had. So hope you guys are clear about the like sources up to PLL sources, or like any other sources that were there, right? So if you guys are not clear, just like let me make a quickly one circuit, like V for voltage. Then let's say if we press one, D, so that will take a diode, and let's say we'll put a resistor, and then G for ground. These components you can take it. These components you can take it from. If I have removed somebody, please try to join again, because I think I missed it. These components you can take it from here. Okay. And this is where. So I am using shortcut because it is very easier. Okay. And I have given you the list of all the shortcuts in the sheet. And it is very user friendly. Okay. So you can do that. And this is how the circuit is made. You should make sure that all the components are having some values, otherwise it will not run. And you can just right click to give a value. So let us say I'm going to give 5 volt. You don't have to give the SI unit for any of the component. That is very common. Okay. If you have to give some other value like 5 millivolt or something, you have to give M. Okay. Otherwise, you don't have to give for SI units. So let's say 1 kilo ohm. The LTspice has very good feature, like they will be able to give you an option of selecting particular component like MOSFETs, op amps, diodes. So those are very specific components. So you can select them. Otherwise, a default value of diode will be running. So let me just run as it is, then we will see. If you are running first time, you can configure it. Otherwise, if you run, then also it will go to configuration only. Okay. So you configure it. It is asking for a stop time. Let me give one, let's say 10 millisecond. I'll start saving data from, let's say, a starting point like 0. If you want, you can flip the, like these windows by this. Okay. So, and press a space bar to fit the complete circuit. So this is how it will work. Now, if you put your cursor here on the, like on the wire, then it will give you the some other pen type symbol. So it is 5 volt which give you. Similar to that, what is the voltage here? That also it will give you. Maybe it will be less by 0.7 volt. So yes, it is 4.3 something. Okay. So by 0.7 volt, it has reduced. If you want to see the complete voltage range, you can just right click on this scale and make the top and bottom scales. So let's say I want to start from 0 to, let us say, 6 volt at a step of 1 volt. So it is giving you 4.3 and 5 volt. Got it?
Doing now.
Right. So this is how it works. Similar to that, if you want to have another voltage source, what will happen? Advanced, you have pulse sources, sine wave, all these things. Let's say sine wave will give you amplitude, let us say 3.3 volt. Frequency, let us say 10 hertz. You can give more also, not a problem. Delay, let's say I will give you 0, and anyway nothing is required. So this has been converted to sine wave from a DC source. Now if you rerun it, you can see this is running, but since it is 10 Hertz, so I have run it for very less time. So I should increase the simulation time. Okay. So let me go here, configuration, increase the simulation time by, let us say, 10 Hertz, right? So it means 1 second, 10 pulses. So 0.5 second I will run. So 5 pulses I can get easily. You have to calculate that. It's very common practice. So you can see I have 5 pulses blue colors, and the red color is uh, clipped voltage, right? At this. I also told you this is not giving you very clear idea like which node voltage is this one blue color and which one is red color. So instead of that, you can name those nets. So go there or press N for net label and put it like V in, press OK. And this one you have to connect it. Okay. So wherever you place, it will get connected. So this one I will connect. It will not go off unless you press right click or you press escape. So I will put one more here, but I'll just right click and change the name. So V out. Now I'll rerun it. It is coming V in, it is coming V out. Understood? So this was the circuit. Now let us quickly, do some MOSFET circuit maybe, or transistors and all. So what shall we do? Any question till now, or have you guys practiced? Like, if you have any doubt or something, you can ask. Otherwise, we'll proceed with circuits. Or one more thing, like if you guys are comfortable with LTspice, we can skip this part and move to components. But let me give little circuits, otherwise it will be a problem. Okay. So I'm going to just save it. See, this will be saved in a default name draft 1, 2, 3, 4 like that. Okay. So it might be very, uneasy or very problematic to retrieve those files. Like while opening, you will not be able to find out the file name, right? So better always have a practice of file save as. So I'll just put it diode circuit. Okay. So now it is named as diode circuit. That's all. Let's quickly take another circuit, new one. File also you can go and new schematic you can take. Let me put component. Yeah.
Can I ask a question?
Yeah,
One thing
please.
you have in common in LTspice is how to add component tolerance because the components that you're simulating, those are ideal components. But in real life, you have 1K resistor, 5% tolerance. So is there a way we can add that in LTspice?
You want to add a separate component, a diode component, something like that you are
No,
saying?
no. What I mean is, how can we add a component tolerance in LTspice? So for the resistor, how come you don't add any tolerance to it?
So let's do that thing a little later. Okay. I mean, what I am teaching you here in LTspice is very basic, and throughout the time you will be having a little bit complex circuits. But having those tolerances and putting all those informations, so that itself will take around around some 20 classes. We have a very good session on only LTspice, and it has like Monte Carlo principles or worst case analysis, and you will be running your circuits around 100 times for different values of resistors. Okay, so those things are there with us. What I'll do is I will send you the materials itself so that if you can take it. Otherwise, that will take it offline. Okay, because that will
So
be very
sorry,
specific. Yeah, that will be very
what you're
specific.
saying
Okay?
is that is a different course.
Yeah, that can be. I mean, I'm just concentrating on the microcontroller parts in these sessions. Okay. But these are needed because when once you design some particular circuit, what happens is you will be putting a lot of sections, and those sections need to be verified before putting into the actual circuit. Okay. So, so if you want to put it in actual circuit, you will be trying to do a simulation, and that simulation here it helps you whether the circuit is right or wrong. So let me just select help you to select the actual diode. So you go to diode, right click it. It is giving you an option of pick new diode. So this pick new diode, we have like very wide range of like values. You can drag it at the corner and you can see lot of diodes are there. Okay. So whichever values, one thing I can tell you for your diode, like let's say your actual diode is not available in this particular series, try to have an equivalent part. Let us say if they are telling you 40 volt, you take it 40 volt, and like average is 1 ampere. So it might not be this diode, but it will serve the purpose. There will not be much variation in the models. Okay. So that way you can do the actual simulations. And now you will see, let's say V in, then V out. So you can see the drop is less. So how will you see what is the drop? You go to this V out. So you will have a cursor. Once you click on this V out, you will have a cursor. Okay. So this cursor is where now if you see peak voltage is how much? 3.12. Okay. So 3.12 means 3.3 minus like 0.2 volt drop is there. That's it. So this particular diode data sheet, if you go and you match it, it will be giving you 0.2 volt drop at nominal temperature. With increase in temperature, you have different. So while select, while component selection, I'll tell you what is the characteristics of a diode. All right. So this is how we do the, selection of the particular component. Now let me do a simple, what is that? Transistor circuit. So let us
Just
say,
one more question. In
Mhm.
regard, so are we still learning component selection or this is LTspice?
uh, Jonathan, like this LTspice is, as I already mentioned, let me open, PPT. See, let me clarify you guys. What we are going to do is, as I already told you in the beginning itself, LTspice is going to support you for validating your circuit. Let us say you have n number of circuit in your, microcontroller board. Okay. Like you have, I mean, you are getting it, what I'm trying to tell you. Like n number of circuits are there. Let's say you have some ADC circuits, you have some voltage divider, you have some, like voltage reference ICs, you have some regulators for power supply. So all these you cannot blindly design and put it into your PCB and go for layout and all those assembly and all, because this might not run. So, and these days companies are very, very, uh, cautious about this. Like they want their PCB to run in one time. Like first time itself, it should run. That's what they're expecting these days. So in that case, LTspice like simulation tools helps you to simulate that and tell you the actual information. Let me give you one simple example and you will understand it. Maybe these small things are not needed for you guys. I'll make it little complex. Okay. So let me put one circuit. Let's say ADA 4528. Okay. So let's say I'm going to put this op amp, and this op amp you can place it like this. Okay. So that is one thing. And you have positive supply, negative supply, output, and all these things are there. Okay. So what you can do is either you can do it by yourself or do it by uh, open example circuit. Okay. So let me quickly do it by ourselves. Okay. So what we'll do is two voltage sources we will add, and let me move it little this side, And what shall I do? Let's say I'll add it a voltage source here also. And what else? I'll put a buffer. Okay. And this is going to be my output. Now I'll just put it that this one as E plus and this one as V minus. Okay. And this one I'll connect. Got it? And this one I'll just put it, let's say 2.5 volt or something. And this one I'll put it minus 2.5 volt. Since I am putting minus, so this only will be the output. Okay. Now this will be, let's say, ground, and connect it. Now this much time you took to just make this circuit, but LTspice had given you very like nice feature of doing this job very nicely. Okay. This one will be V plus. So what does it mean is you don't have to actually connect directly here V plus, okay? Or otherwise you remove this net and directly connect this one. This will do the same purpose. Like this net name is actually connected to this one. And this net name is connected this place, okay? And then this is your ground, which is going to get connected here. And this. That's all. Now what I'm going to do is I'm going to simulate and show it to you how it helps you. So let us say voltage is there. I am going to have a sine source. Amplitude is, let's say, 0.1 volt, okay, like 100 millivolt, and 100 kilohertz I am going to take. Okay. So 100 kilohertz, so like input is there. Now if you run it, it is asking for how much time shall I run? So 100 kilohertz is going to be how much millisecond? Like 1 kilohertz is 1 millisecond, right? So it will be 0.001. So let's say 0.005 millisecond I will run. It's up to you, like how much time you want to run. That's not a problem. Now let's run it. So, oh, this is too much time I have run. Let me reduce the time. 5 milliseconds. Only one pulse came, right? So I'll just make it, let's say, 5 milliseconds. Oh. Okay, so this has run, right? Now, if you see the output is slightly deviating. You can see, right? Slightly deviating. It will be much better if you can see, let's say, some 3-4 pulses, then it will be much clear. Okay. So you can see it is almost overlapping, and we are supposed to get this. We are not supposed to get something else. Now you increase the like frequency to 200. So this nobody can tell you. Let's say your input frequency is 200 kilohertz. This IC is how much capable of? I think some 2 megahertz or something. That you can see by right click and see the like find at analog.com. It is telling you. So if you open this, it will tell you like what is this particular IC. Okay. Yeah, so it is telling how much there will be bandwidth. Yeah, 4 megahertz. So 4 megahertz means what do you expect? It should it should work at least like up to 2 megahertz or 1 megahertz, right? So that will be my understanding. Like gain bandwidth product is 3 megahertz. So I will try to work up to like 1 megahertz or something. So that is it going to give me that information or not? That we will check through the through giving the input voltage, right? Now, let me just make it, like 700 kilohertz. Okay. Or 200 did we saw or not? Yeah. So little bit shift is there. You can do one thing, you can directly drag like this. So little bit shift is there. Now I am not going to do the another circuit. What I'll do is quickly, I'll just put one component, okay? Let's say LT2051, okay? So this and I am going to put open example circuit, okay? So this is also going to give almost same result, right? Now I'm going to run it and show you like how it works. So see, this is my input and this is my output. So if I increase this source, let's say I make it, how much is the right one? 700 kilohertz, right? So I'll make it 700 kilohertz. Okay. Now run it. I should run little lesser time. Hmm, let's say 0.01. So see, this is distorted. This guy is not distorted. For 700 kilohertz, this is giving you very nice result, but this is not able to give you nice result. Are you getting it? Like if you see what is the period that we have run it for 0.05 and what is the period we have run it for this one. Let's say we'll run it for 0.05 only. Okay. And run it. So now you can see this is distorted. The output is distorted. I mean, the problem is we have designed not the unity gain. So we'll just cut this so that it looks exactly same. And cut it. Okay. So exactly same circuit, right? Now, if I rerun it, so my input is this one and my output is still distorted, right? But here my input is this one, my output is not distorted. So now you tell me, any of you can raise hand and tell me that which IC or which op amp you will you select for your application, for your design.
The ADA 4528.
Yes, because LTC2051 is not giving the correct result, right? And why I'm telling you, like you can see very quickly LTC, what is the signal bandwidth and all those things. So it will give you the same almost, right? LTC205. Or I don't know like how much is the bandwidth. What is the bandwidth here? Not shown here. Huh? Somewhere it will be there. So you are getting it like ADA is giving you like this. I mean very nice result, and this one is not able to give you that much nice result. Okay, so this is the change that we actually see, and this cannot be like verified after getting the board. This has to be simulated and verified, and then only you can utilize this particular. See, this is also having 3 megahertz gain bandwidth product. See. That is the reason I gave you this example that this IC is claiming that it is having 300 megahertz gain bandwidth product. Similar to that, ADA is also claiming that I am also having 3 megahertz gain bandwidth product. Now you guys tell me both are claiming same. Why not I use LTC 2051? That's what I thought. But I'm getting bad result with this. So I will not use this. That's all. But you don't have a choice when you have your input voltage is going to be higher because this is capable of up to 36 volt and this is capable of up to 5.5 volt. So hope you guys are now clear. Okay. Like this, you can simulate your circuits by just placing a component and instead of making circuit by yourself, which I just now taught you very nicely. Okay. You can open an example circuit and make those changes. Okay. Any IC you want to search, you search it here. If it is available, it will be there. Got it? Let me take another circuit. So you can cut it. It will ask you to save. I am not going to save this which I have opened as an example circuit because I don't want to disturb their circuit. Okay. You want to save the changes. What you can do is you can go and save as, and then you can do that. Okay. So it is always suggested. Okay. Now let us remove this. Let me give you one more example and then we'll quickly proceed to other things. Let's say I want to, simulate some regulators. So tell me any name you guys remember.
7805, 7812.
Those and all I'll not take right now. I'll go ahead with little newer one. So let's say ADPL 42005 I'm going to take. Okay. So if you want, you can place this, part and do the design. That is one thing. Okay. So let me open very easily for you. Then you will understand very nicely. Yes. Okay. So see, this is having a, a 500 milliampere capability, up to 20 volt input it can take, and it is very low noise application for a lot of, like a medical device, industrial instrumentation, and all those things. It has one is fixed one and one is adjustable one. So fixed one will not require voltage output setting dividers like resistors, and this will require those resistors. But what I want to do is instead of doing the calculation and all those things, like let us say, let us say, I'm going to do here calculation here that what is my input voltage, what is my output current, and what is my output voltage. And based on that, I am going to do the thermal resistance is 48.5, which is taken from IC data sheet. But this will be changing for you because once I teach you the regulators, it will change. Okay. Because you are going to, maybe you are going to design the regulator in lesser space than what they have recommended. So the power dissipation will be more. So it won't be able to give you. And with this information, my junction temperature is reaching to 101, which is lesser than 125. I'll just put it less than 125. Then it is capable. But now let us say if my input was 12, the temperature has reached 271. So IC is telling that it can take up to 20 volt input and it can give you 500 milliampere output. But this is not true for all the input and output ranges. Okay. And this is the thing that you can do here as your own calculation. That's called designers. The same thing can be done here as well. Okay. So let me open example circuit. I don't want to waste my time to redesign the circuit. So I'll just put it like this. Okay. So now say input voltage is there, output node is there here, and we have capacitor, load, everything is connected. So load, maybe if you guys can calculate, like output is set to 3.3. So 3.3 divided by 8.6 is going to be 383 milliampere. Maybe I don't know what is the output voltage set here. So we'll see quickly. So let us run it. I'll keep it like this. So what is the input voltage? 6 volt. Okay. Now what is the output voltage? That is reaching to 4.2 volt. If you want, you can take a cursor here and quickly, do that. Okay. So see, cursor has come into this screen. So it is 4.25 volt. Okay. Vertical. So this is the setting that was done for this particular resistor settings. Now, why don't we do one thing here? What is the current that is flowing? So current I have told you to see, right? You place your mouse across the component, so it will change to that wheel type. Okay, and then you click. So current will come. So see, I load has come. Okay, IR load has come, and you can see it is going up to 500 milliamps. So if you want, you can do that and see it is coming how much current. Okay, so it is coming 496 milliampere. So this IC is capable of giving you for 6 volt to 4.2 volt output. So if you want, you can write a note here, text 6 volt to 4.25 volt regulator, 500 milliampere. Now, shall we make one change? Let me do one thing. I am going to take the adjustable one. I am going to take input as 5, output as 3.3, and my resistors values will be how much? 59.4 R2. R2 is which one? Down one is.
Sir, I have a question. You see, for
Yeah.
the Excel spreadsheet, are we going to learn how to make this?
Sorry?
Are we going to learn how to make the Excel spreadsheet?
This Excel sheet we will learn to make. Yeah. I'm not teaching you
Okay.
right now. Once we design the circuit, application circuit, we'll learn. Okay.
Okay. Yeah.
And just simulating the circuit. Okay. See, unless you see, one more thing, guys, I'll tell you. Once you become little bit experienced, like let's say 5 years or 6 years, right now you go and like select this particular what is that regulator and design a circuit and give it to your manager or somebody. Nobody will agree. They will tell, I cannot take this circuit. You have not given a capacitor, you have not given proper capacitor value here. How they will believe that this circuit will work? Do you guys understand? So for that purpose, this is what I will do. If I am there, I will do one thing, that I am going to give a space here little. I'm going to give a space here also little. Put little like capacitor extra. Where is it? Put here capacitor. Okay. And then give grounds.
This is a sample circuit, right, sir?
This was sample circuit, but I am redesigning it.
And that means
Because
it's already tested and verified.
No. Madhusudan, the thing is, this is tested and verified. I agree with you. But based on my experience, I have observed that you give your, like a required amount of capacitance at the input, required amount of capacitance at the output. The data sheet, what they mention is the very minimal requirement that is needed. Okay. So see here, he is claiming that 1 microfarad is needed. Why he has not given any capacitor at the input in this simulation circuit? Because he is assuming, that my voltage source is there, which is infinite source. Means it can give you any amount of load that you need. It will never go deep. Okay, so that's not the case. Understood? So I will just put it, let's say 10 microfarad here. Let's say 0.1 microfarad. So today, guys, I will tell you guys, like if you're designing a linear regulators, try to keep 0.1 microfarad filter capacitor in addition to your bulk capacitor every time. Okay. These days, actually, the ICs are including inside these two capacitors. I mean, this 0.1 microfarad capacitor, and now they are claiming that we are designing a LDO without capacitor, like capacitor free, because capacitor takes little space. But those are suggested for only mobile application and all, where the space constraint is a lot, like you have variables and all. And can we quickly make this change? Like I
So
told you, what is
why you
that?
are keeping that
102.
0.1 microfarad capacitor? Is it because of to reduce the effective series resistance?
No, I am using this is also ceramic capacitor, so it is already having low ESR. Okay.
Okay.
Yeah, so that
And
is not the situation. This is
but
like what is that? High frequency noise filter. Okay.
Okay.
Lower the value, higher the cutoff frequency. So I'm going to put it 5 volt, and I am going to make changes 59.2 kilo ohm and 102 kilo. So let us see whether it is same or different, huh? So my output V out is how much? Let me just see here. So V out is 3.32. Got it? So I designed this particular circuit, and see what I did is R1 was calculated 101.27, but I have selected a standard value during the resistance selection. I told you guys like 101.27 will not be available. So I'll take a standard value from E96 series. So that I have done here. And then based on this selected value, I will have another output calculated. Actually, this value I calculated based on the output set value. But actually, I am going to design for 3.31. So it is almost coming 3.31. See, 3.32. Understood? So I hope you guys understood like how to design this. And yeah, see, this is output, sorry, input. This is output. Yeah. And where is my output current? So output current is around, let me just see that. Output current is 386 milliampere. Okay, you can increase this and see what is going to happen. So let me do one thing. This is 54, right? What is the capacity of IC? 500, right? So if I put 500, it is coming 500, like it is able to give you, right? So what I'll do is, what is the resistance required to get 500 milliampere output? What I'll do is equal to 3.3 divided by 0.5. So 6.6 ohm. So what I'll do is my load I will increase. So I'll increase it to 6.6 ohm. So are you getting it, like how to increase or reduce the load? So you understood that. And now what I'll do is I'll rerun it, and this green I load will change to 500. So see, it has now changed to 503. Understood? Now, other things what you can do is, while like redesigning the circuit or simulating the circuit, you can go here, the source, and you can go to advanced, and maybe you can do, let us say, what is that? Oh, we don't have here. Here we have PWL file. Step function is not there here. You can do that also. Let's say initial voltage is 0. V1 is, let's say, 5. T delay, I'll give you just 1 microsecond. And T rise, let's say 1 microsecond. And T fall 1 microsecond. T on time, how much time do you want to? Let's say 100 millisecond I want. And switch off for 100 millisecond extra. Or let's say switch off for 200 milliseconds. So period, I'll make it 300. So 300 millisecond I am running. So how much the time I should run? 300 into 3. Let's say 900 millisecond I'll run. Okay. 3 pulses I want to run. Now what I'm going to do is, this is going to like load this IC little bit, like higher. So let me do that. Now you can see my input voltage is changing from 0 to 5 volt for 100 millisecond, and again changing to 0. Now what will happen at the output, that we will see. So output is going from 0 to 3.3, coming back to 0. So there is no, like ringing or something at this place. You can see, you can place the cursor and keep, like dragging. So it will become like this. Now zoom to fit, so it will come. Okay. Then what is the current that is flowing? So current that is flowing is 500 milliampere. So this is how you decide the simulation as well as the calculation. Okay. So I'm keeping up to to this, what you guys can do is, you guys can try to, like simulate your circuit by yourself. Like keep a transistor, keep a current source, and keep the resistor, and put a voltage source, and see the output whether this is coming or not. So these are very, like basic levels. So you don't worry about this, but these things you can do. These circuits we try to utilize in our, industries a lot. Okay, so can you guys, like if you have your file open, can you guys simulate this circuit? I'll give you this.
Sir, in the previous circuit,
Yeah.
We have one capacitor recommended from data sheet,
Okay.
C1 or the C3.
Mhm.
So one more you added, right?
Mhm.
How much value we have to add? How to figure it out properly?
That we will see when we start circuit designs.
Okay.
Yeah. So you guys can quickly simulate this and see whether you are able to get the switching proper. Like here I have told like input, output, and all these things. So this is V out. It is mentioned here. Okay, the red color. The input is green color. Okay. So if you guys can get this. Now, since this circuit I have designed it, what I'll do is I'll do a save as and ADPL 3.3 volt or 3.3 volt 500 milliamps. Okay. I'll remove this 5 volt. So this became your circuit now. Try to use, guys, like if I mean apply, I mean see this analog devices has come up with very nice feature these days. They are giving almost all the components. So do not give a, like what is that excuse that we do not have a component in the library or something like that. So if it is overlapping, you can keep it little down. Okay, that is always a good practice. Keep the response here. Okay. All right. So let's, I will just remove this. So place a component, right? So P for place, I will take NPN transistor. Then what I need resistors. So I will take one resistor here. Let's say one more resistor I will need at this place, let's say, and one more I will need at load. Then we need one voltage source for this place. And one current source I need. So I'll have to go here. And this is my current source. If you want, you can put a voltage only. That is not a problem. Okay. So I'll just put a voltage only. Try to take. And let me just take one more resistor as a divider so that if you have voltage a little bit higher, uh, what will happen is you can do that. Understood? So this is my circuit elements. Put a few grounds so that you can quickly, like complete your circuits. So, and then this is how you can make. And I'm telling you guys, try to do these circuits because what happens now, actually you think like circuit is very easy, but you will not be able to, let's say, simulate and get the result. Okay. So simulation, if you are okay, you don't have to waste a lot of time in designing and verifying that if the circuit goes into my circuit, whether this will work or not. Okay. So let's say I'll just put it 1K. And this also I'll put it 1K. I am going to put this as a pulse source so that I'll make it on and off. So initially I'll keep it 0. On, I'll just keep it, let's say 3.3 is enough. Okay. Time delay, I'll just keep it 0. Let's say 1 microsecond. 1 microsecond. T on time, how much will I keep? Let's say 100 millisecond I'll keep. 100 millisecond off. So this is period. That's why 100 into plus 100 is 200. Now, if you guys can calculate, it is fine. Otherwise, I'll just give a random value right now here. So let's say 220 ohm I am going to give. And here I'll just give a little bit lower load. So lower load means let's say 1 kilo ohm I'll just give. And this one I'll keep it as, let's say 5. If you want, you can keep V, otherwise you don't have to keep because it is a unit. Now, this is a default value that I'm going to keep. So what I'll do is I'll directly run and see what is going to happen. So what is the period? 200. So I'll run it for, let's say, 3 pulses. So 2 3 is 600 millisecond I will run. So if 600 I will run, then 3 pulses will come. So it's up to you, like how much time you want to run. Okay, it's totally up to you. Nobody is stopping you. Now let's run it. So if you see, this is my input voltage, which is plus minus 0 to 3.3 square wave, right? And then we have the VBE, that is going to be how much it is? It should have okay. So it is coming this from V to BE. So it will be 0.7, right? So it is coming 0.7. Okay. 0.7 or 0.8 will be there. And then you see the output. So output, what will happen? Whenever this is on, I mean to say what? Whenever this is high, what will happen? This guy will get sorted, like it will go saturated, right? So that time V output will be 0 actually. Understood? And whenever this is off, output will be running, right? So whenever this is high, my output will be actually low. So see, the green color, whenever my red color is, or let's say blue color, whenever my blue color is high, like 3.3 volt, my green output is low, which is settled to 0.2 volt or less than that. Okay. So everybody agrees to this. So this is how switching circuit can be simulated. Now, for your information, you can select a particular NPN transistor for your sake. So go to right click. We have an ample number of transistor available in the library. Now, if you do not have your choice, the like component, you can raise a request at the analog devices website. I mean, last day I told you, and go to help and raise a request. Can you please add this particular component? This will be much faster than creating by yourself. Okay. And you can take, let's say, I will take BC at 47. Very popular. So I'll take this. Now it will change a little. You see the difference between these two. Let's say I'm going to keep a copy of this, okay, and see what is the change that is going to happen. Now you rerun it. So now you see it has shifted little differently. Now, can you guys tell me, if a good designer is there, this spike is coming. So this spike, I want to remove it. Okay. So how shall we do? So for that, you will be putting a capacitor or something like that, right? Bypass capacitor, so that it can be removed. So this is how you do the circuit. Okay. Good. So this was about, like a little bit that I wanted to teach you guys. Similar to that, like transistor, we have MOSFET. So whereas MOSFET will be this, give a RG, I'm sorry, like gate resistor, and give your VDS voltage and see whether output is switching properly or not. Okay. So this is a characteristic actually. MOSFET as a switch is shown here very nicely. So you can see we have enable signal coming here, and whenever it goes high, what will happen? This guy will get sorted. So at that time, V out will be 0. So you can see whenever my V enable is green one. Okay, so V enable is high. My V output is red one, which is going low. Understood? So this is how it is happening. So please, a very humble request, all of you design MOSFET and transistor as a switch, both NPN, PNP, and NMOS and PMOS. Okay. How to select the component? I'll just quickly tell you again. Go to a new circuit, press P for like components, or if you do not know, this is the component symbol. Okay, so this is the component symbol. Here type NPN, NPN will come. Okay, so NPN is there. Then type PNP, PNP will come. Okay, and type P again, NMOS. So NMOS will come, and type PMOS, then PMOS will come. So we have total 4 circuits. So this will be the task to complete as a switch. Okay. I'll give you the reference also. Don't worry that, I mean, if it is not possible, you can refer that. Okay. Exact circuit I'll give you. But do not depend on that. That is the request. Rest. Next, there is, like very nice circuit that we always utilize in battery powered components. Okay. In battery powered system, what happens is you have, let's say, 12-volt battery or 24-volt battery or 48-volt battery. These days, so batteries capacities have increased like anything. Yeah, battery capacity has increased like anything. But I'm just going to show you a very simple circuit. Okay, so let's say 12-volt battery you have connected in a medical device, and this is connected to the system. Okay, system load. Now the problem that happens is if I directly connect the battery and it is going to power up the circuit of a, let's say, patient monitor or any other, what is happening is it is going to drain the battery very fast. So to avoid that, we have, let's say, like a circuit which can, switch off or switch on or something like that. So for that, what we do is, let's say controller is trying to switch on and switch off this power, or, like switching this input power to output side. So what will happen? This particular MOSFET will be a signal MOSFET, which will be very small MOSFET, which will go short, and this will pull it down. Once it is pull it down, then this power V input will go to the output, and this is how it will power up to the load. And whenever it is not required, what I will do, I'll make it low. I mean, make it low. So it will be open, and at that time it will be powered. So it will not switch on, and this V output will not be there. So there will be very less, like a drainage of this power. Okay. So this is very important circuit. Every time, the only problem with this is selecting this particular MOSFET is a big task, because this MOSFET require a lot of, like a specification, like what is the current rating, what is the voltage rating, or, like, I mean, what is the power dissipation capabilities. So all those things are needed while selecting this. Coming back to op-amp, we have already seen the circuits. Okay, so you can always design your own gain and all those things. And this is very, very important circuit. I'm telling you, like go to this LTspice, select your op-amp, and design your inverting amplifier, non-inverting amplifiers, or, like make a buffer. All those, see what is the delay that is happening from input to output. So all those things you can see very nicely, and then you can propose your circuit to your like team. Okay. Now let me give you an example of Zener diode circuit. So that is important. What we'll do is I'll take a new circuit. And let's say I'm going to put a voltage source, a limiting resistor that will be required, right? And a resistor as a load, and a Zener diode that will be needed. So for that, what I'll do is I'll place a component from component window by pressing P. So this is Zener. You can write it Zener, so it will come. Now, can we quickly route this? So once we wired this, what is going to happen? We'll get connected like this. And if you guys are aware of how the circuit works, I'll just quickly tell you also. Okay. I hope this circuit is okay. I don't need to place two ground, so I'll just delete this. Press delete button and you will be able to delete this. Okay. Okay. Now, let me give you introduction here itself. Okay. So what I'm going to do is, you already know that this is my input voltage. Let us say if my diode would not be there, then what will be the voltage Vx? So Vx will be, you already know, 12 into R2 by R1 plus R2. Let's say R2 is this and R1 is this. Okay. So it is going to be how much? 12 into 1 by 3, that is 4 volt. Now this Vx is coming 4 volt, which is lesser than the diode capacity breakdown voltage 6.2. So it will not come into picture. So my V output will be actually 4 volt. So you can see my V input is 12 and V output is 4. Okay. Now this will act as a regulator when my output output this one without this thing is appearing more than that. So let us say I am changing this resistor to 500 ohm. So in that case, what will happen? It is becoming 8 volt, which is greater than 6.2, and that's why the output will be clipped to 6.2, not 8 volt. Okay, let's do that. Let's say 12 volt, and let's say this is 2 kilo ohm, and let's say this is 1 kilo. Select a diode of your choice. I don't mind it, whichever diode you select. So I'll just select where is my breakdown voltage. Let's say 6.2 I'm going to select. Okay. So many are there. You can select any. Okay. And if you want, you write it for your reference so that, like, you don't forget what is the voltage level there. Now, shall we run it? I'll just delete these. Okay. One millisecond is enough. So see, my voltage is 12 volt. My output voltage is how much? 4 volt, because it is less than 6.2. Now my output voltage I want to increase. So how can I increase? By increasing this resistor, right? So how much shall I do? Let us say 20K I will do. I don't know how much it is going to be, but let's see. So now it is regulating to 6.2 because this voltage is more than 6.2. Understood? Now, can we do one more thing? let us change the source to some sine wave or pulse wave. Okay. Sine wave, I'm going to make it, let's say 12 volt peak, and frequency, let us say I'll give 10 hertz, and delay I'll just keep it 0. Okay. Now, if I run it, what is going to happen? I have to change the actually time period. So 10 hertz means 1 by 10 millisecond, right? Sorry, 1 by 10 second is 0.1. How much shall I run? 0.5 second. So see, what is going to happen? My input voltage is actually complete plus minus 12 volt peak to peak. My output voltage is clipped to 6.2, and negative side, it is not working at all because it will be, working like this. So it will be sorted. So that's why it is coming almost 0. Just the drop voltage is coming, which is 0.7 volt or something. So if you want, you can take the cursor and see what is the voltage level at each location. So let us say, where is the cursor? Coloring is very bad on this, so 6.2 is the output that is there, and in negative side, it is 0.8 volt. Okay, so that's nominal. Okay. Want, you can change this particular diode to some other values also, not a problem. So what values do you guys want? There is no other values, only higher values are there. Okay. Let's say I'll just keep it 6.8. Okay. So now it will clip to 6.8, not 6.2. Okay. So let's rerun it. And you can see this is clipping to 6.8. Oh, sorry, where is it? 6.8. Okay, vertical. Got it. All right. Any next is diode circuit. You can practice by yourself. Lot of them are there. Parametric I have already taught you guys, like how to set the different values of resistors or some, or like the diode, and you can see. So see, I have done here a parametric Zener diode. Like the Zener diode was given BZX84C10L. So I have given values, list values like 10 volt, 12 volt, and 15 volt. So this is how diode modeling you can do. Okay, you guys were asking diode modeling, but you can do this, so not a problem. One of the component I have selected, but I am going to force, this is 10 volt diode, but I am going to force this diode change to 10 volt also, 12 volt also, 15 volt also. That's also, this was all about, LTspice. I'll keep it up to this, and then we'll move to component selections. Any question? All right.
Yes, sir, we'll practice.